In the following, we will demonstrate XAI4EEG, our application-aware approach for an explainable and hybrid deep learning-based detection of epileptic seizures in multivariate EEG time series. From the technical perspective, XAI4EEG encompasses EEG data preparation, 2 deep learning models, 1D CNN and a 3D CNN, and our proposed explanation module visualizing feature contributions that are obtained by 2 SHAP explainers, each explaining the predictions of one of the 2 aforementioned models. XAI4EEG is operationalized using the Streamlit package and is accessible online. Please find the web link and the link to our GitHub repository in the description. To evaluate XAI4EEG, we used an EEG dataset comprising neonatal recordings with seizure annotations that we modeled as a binary classification problem. In our case, the multivariate EEG data contains 18 univariate time series, 1 for each signal of the 18 electrodes. We subdivided the continuous EEG data into non-overlapping intervals with length of 15 seconds. Seizure detection and explanation is done on the basis of these intervals. For demonstration purposes, users trigger the data preparation, model prediction, and the visual explanation by selecting one of the 20 intervals via the select bar in the top. In this demo, we choose interval number 14, a ground truth seizure. Differently from normal EEG patterns, seizure onset causes electrographic discharges and spikes in the signal that are visually detected by medical experts. In this interval, the seizure becomes concise within the second half. Besides the raw EEG signals, we display the preprocessed and transformed EEG data of both seizure detection methods. For the 1D CNN, the interval is split into 15 subsequences of length 1 second using a non-overlapping window. Thereafter, the EEG data is transformed into the frequency domain and is displayed in tabular form, showing the subsequences power spectrum of the 18 electrodes. There is a substantially higher spectral power in the interval's second half across all electrodes. For the 3D CNN, the EEG data is transformed into the time frequency domain by creating time frequency maps using Morlet wavelets. These time frequency maps hold the duration of the extracted interval on the x-axis and the frequencies on the y-axis. The color corresponds to the EEG power. Note that low energy is colored in blue, whereby high energy is colored in green. Hence, even before prediction and explanation is done, users can compare the patterns in the raw and the preprocessed EEG data. At the very left and at the very right, respectively, we locate the predictions of our interval-based classifiers. Here, both correctly showing detected seizure. In the middle, we locate the visual explanations for both model predictions. All are based on our proposed explanation module that displays the feature contributions, in our case, SHAP values, and that is linked to the raw EEG signal representation of the monitoring system. To compute the SHAP values of the classifier's predictions, we choose 2 post-hoc explainers from the SHAP package. The first is SHAP Deep Explainer. The second explainer is SHAP Gradient Explainer. The explanation module is based on a grid of size 15 times 3, holding the length 15 seconds of the interval on the x-axis and the 3 frequency bands on the y-axis. While the x-axis constitutes the explanation in the temporal dimensions, the y-axis explains the spectral dimensions. We propose a novel flow of patterns to map the raw SHAP values to the explanation module. Hence, each of the 45 cells represents a spectral temporal EEG region holding the respective SHAP value and is colored in red, inspired by the idea of heat maps. The more intense the red, the more this spectral temporal region contributes to the final prediction. The explanation in the spatial dimensions arises from obtaining the feature contributions per electrode and is referred to as electrode-wise explanation. Since EEG time series are characterized by spectral, spatial, and temporal dimensions, and all are crucial for seizure detection, we argue that an explanation of an algorithmic prediction must encompass these three dimensions. We propose a validation workflow to validate the classifier's predictions, where users contrast the returned explanation patterns with the electrographic patterns of the raw EEG signal and the preprocessed data. For instance, the visual explanation for the 1D CNN point to decision-relevant factors in all the three frequency bands in the second half of the interval, around 7 to 8 seconds, where the seizure became obvious. Moreover, the electrode-wise explanation highlights, for instance, electrode F4 and F8 to have a higher marginal contribution to the final prediction than, for example, F7 or F3. This could be due to the origin of the seizure in the right lobe. In addition to that, the visual explanation for the 3D CNN also highlights the first half of the interval to be important. XAI4EEG highlights both agreeing and disagreeing patterns, increasing overall trust in the predictions. Our explanation module cannot eliminate the disagreement, but highlights it for inspection by the medical expert. This constitutes an advantage of our hybrid seizure detection approach that incorporates an identical visual explanation schema, where one learning module may miss to capture and therefore to present decision-relevant factors, while the other learning module does and therefore augments the overall explanation. In addition, this constitutes a way for evaluating an explanation.